dt, right? Because it's just 1 if I take the derivative of t. So I don't have to multiply by anything. So that's nice. But then it would probably also be helpful to write it as t minus 1 to the what? 1/2. And when we do that, now we can add 1, and we get like what's the antiderivative of t minus 1 to the 1/2? So if we add 1, we get 3/2. So I would have t minus 1 to the 3/2. Yes. And we would also be dividing by 3/2, which is the same as multiplying by a 2/3. But I already have a 2 out front, so what are we going to get? 4/3. Yes? But this is an indefinite integral, so what do I have to add? A c. How many c's are we going to have? 2. So, you can either 1, label as like a c and k, or 2, more common notation is to have a c sub 1 and a c sub 2. Because both of our components need a c, and they are not the same c. So we have to make sure that we label them differently. And then for our second part, what is the antiderivative of sine? Negative cosine. And then we're going to have plus c2. Not scary, right? For our next one, what are we going to have to do? This one we do have to do a u sub because I have an e to the negative ct. So what are we going to end up with? For our du, negative, no, for du equals negative 2, right? dt. So we are going to have to divide by a negative 2, so we do get a negative 1/2 in front. And then what is the antiderivative of e to the u? Yep. So I get a negative 1/2 e to our u, which was a negative 2t. Since they gave it to us in component form, I'm going to leave it in component form, so I'm going to put an I there.
Is that interesting?
Yes, sorry. Plus c1 times I, then I. What is our antiderivative of 1 over t minus 1? Natural log of almost absolute value of t minus 1 plus our c2. So all of our normal integration rules apply. We're just looking at them with t's now instead of x's. What questions do you have on those? And if these were definite intervals, the only difference would be is then you would have something to 1, if it's definite, I don't have to have c's, and then 2, you would just plug in your bounds, but into both pieces. Agree with me there. Okay. So this is solving a vectored value differential equation. So I have the vector of cosine, comma, sine. And I also have the initial condition that r of 0 equals 1, comma, negative 1. So what do we want to do first? Take the antiderivative. Okay. What is the antiderivative of cosine? happens here is that we have to solve for both of our c's, right? So notice, what are we plugging in for our x component, or both of our t's?
0.
0. Okay. I'm gonna come over to just the side because I tend to think that's a little bit easier. So what are we setting our x component equal to? 1? Yes? Okay. What is sine of 0? So I get a c1 equals 1. Okay. Still plugging in 0 for my second, but now we're setting it equal to -1. What is cosine of 0? Okay. So what does c2 equal? 0. So we get that, and the final answer. So again, so very similar to how we've always solved for our constants, just now you gotta do it twice. What questions do we have there? Good so far?
Very quiet.
I don't know if that's because we're soaking in all the knowledge. Hopefully. Alright, if a path of a particle satisfies that the derivative of r equals 3t squared minus 6 square roots of t, and we have the initial condition that r of 0 equals 1, 4, what is the particle's position at t equals 4? So what do we want to do here? What? Take the antiderivative of what we have here, because that's going to get us back to the original r. Agreed? Okay. So r of t is going to equal, what is the antiderivative of 3t squared? Uh-huh.
Plus
No. Okay, what is the antiderivative of 6 square root of t? So 4 t to the 3 halves plus rc6. Yes? No maybe? And then what do we need to do? Yeah, use our initial conditions. This one's kind of easy because again, what are we plugging in for? 0. So I'm just going to get that c1 equals 1 and c2 equals 4. Yes, no maybe. So that would be our original vector function. But then what does it ask us to do? Okay, so what do I do? 4. And what is 4 cubed? Huh? 64, and I add 1, I get? Cool. If I'm raising something to the 1/2 power, what is that the same thing as? The square root. So I have the square root of 4, yes? Which is, so the third is 8 times 4 is, and then plus our last 4 is, out of there. acceleration and distance. They should look pretty familiar, because they're pretty similar to our parametric equations. These are also in the packet that I gave you. You don't have to write all of them down, unless it just really makes you happy. But I mean, most of them kind of make sense. So like our velocity, if this is my original function, right? I'm just gonna take the derivative, okay? But again, we have two different parts, so we have to take the derivative of those kind of separately. Your speed, do we remember what the double lines mean? Magnitude. So speed is equal to the magnitude of velocity, which is also the magnitude of our original derivative. And remember that we said that really all magnitude is going to be is the distance to 0, 0. So it's basically our distance formula here, except we're not having to subtract anything because it's the distance to 0, 0. And because from my original, it is the magnitude of velocity, we're taking the derivative of each of our parts and squaring. Again, acceleration is going to be our second derivative, so we just take the second derivative of both parts. And then distance is basically the antiderivative of our speed or magnitude from A to B or wherever we're trying to get to. Because velocity in this case is, again, we're defining a vector, right? Or in other words, a like two-part thing, right? We have an x component and a y component. So notice that v of t still has two components. It's still going to be a velocity or a vector defined function, yes? Stay with me there. However, distance we do not want as a vector defined function. We want it as an actual number. Same thing with our speed. That's going to be an actual number, which is why this is magnitude. So like this is no longer a vector, right? This would just be a number. Now, if it's an equation, it could still have t's in it, right? But notice that I don't have two parts to this anymore, so this would still just be a number. Same thing with distance. I need this to be the distance of my original, not just the vector part itself. Is that going to make sense? Using those physics terms, that's good. There's a reason I stay qualified with physics, but it works sometimes. Alright. So let's get and tie all the things in together now. Okay. So it says an object moves along the plane curve C described by RT equals 3 cosine ti plus 2 sine tj. So the first part asks us to find a rectangular equation that describes the object's motion. What do we want to do? Okay, that's okay. So again, remember our vectors are very, very similar to our what? Parametric equation. So technically, what do we have? My I is my x, my j is my y. Because basically those are our horizontal and vertical components. So we separate them by saying x equals 3 cosine of t, and y equals 2 sine of t. Right? I'm just breaking them apart into their components, kind of like we did with our parametrics. Except with our parametric, they were given to us in this, right? We're just having to switch it to that. And remember, when we eliminate the parameter, what are our two options? Solve for t. If I have like something that's like 3t minus 1, I'm really easy to solve for, and then I just plug it into the other equation to now have it in terms of x's and y's. Is t going to be fun to solve for either one of these? No. So what did we say our other option is? Yeah. Remember, this is where we use our sine squared plus cosine squared equals 1. So we're going to get x squared over 9 plus y squared over 4 equals 1. So I'm going to skip part B for a second. Go to part C. What is that graph going to look like? An ellipse, what kind? Yeah, it's a horizontal, right? Because remember, whatever number is bigger is where it is longer. And we are centered at 0, 0. So we would have vertices at -3 and 3, and co-vertices at 2 and -2. And again, trying to make this look like a nice, pretty ellipse. It's a little lopsided, but that's okay. But remember, what's different about our vectors? What do they have? Directions. What do we also need to add? Arrows. Do we know which direction this is going to move? It should move counterclockwise, right? Because I have sines and cosines, and nothing else is going on. But if we didn't, what could we do? Right? Make an H chart, right? Because we have 3 components now, or whatever you want to call it. So what's a good number to plug in first? 0. What do we get? Cosine of 0 is 1, so we get 3, right? And then sine of 0 is 0, so we get 0. So we are starting at this point, 3 comes 0. Then what's the next easy thing to plug in? Pi over 2. Cosine of pi over 2 now is 0. Sine of pi over 2 is 1, so now we get 2. So notice that we are moving towards this top point, and we will continue in that direction. What?
Is that because it's the same direction when the circle goes?
Correct. It's also just, technically it's because the convention of how we decided to label our things. Like, we label the positive y-axis as pi over 2 instead of labeling the negative y-axis pi over 2. If we flipped those, then they would rotate the opposite direction.
Okay.
Which technically, that's just a convention. So again, if you wanted to flip all of your things, right, you can. Also, it's just a convention that we tend to make our negatives mean to the left and down, but if you needed to, you could always flip that, as long as you describe that in whatever it is you're talking about. And that's just the standard convention that we use in mathematics, but you can technically make it do whatever you want. Alright, so let's go back to part B. So it says find the velocity vector, speed, and the acceleration vector. How do we find the velocity vector? Take the derivative. How many derivatives do we technically have to take? 2. So what do we get there? Derivative of 3 cosine of t is -3 sine t. And that is still our x component, so it still gets the I. sine. 2 cosine is still our y component, so it still gets the j. And then we said that speed is what? The magnitude of our velocity, which means that we take the square root of each of those things squared. So we would get a 9 sine squared t plus 4 cosine squared t. And then again, like if it asks for the speed at time 4, then we're plugging in 4, or you know, whatever it asks you for. What about acceleration? Yeah, derivative of our derivative. So we get -3 cosine t I. And now it's going to be -2 sine t j. Now on this last part, what is he asking for? What's that mean? We are going to draw a pretty picture. We're going to draw some lines. But first we need to know what those vectors are, yes? Which is why it gives you the point 3, 0. So what do we want to do with that? Plug 3 and 0 into what? Yeah, but that. Oh, right. This is a what? Rectangular point, right? This is x and y. Do I have an x and y here or here to plug into? No. So yeah, we would need to convert and go backwards, right? Or we can also go like, does that point look familiar? Yeah, what did we have to plug in for t in order to get 3, 0? 0. We allocated that. Which is why if they do something like this and they give it to you in rectangular form, they're going to give you something that's pretty easy to like relate back to what our original was. Are we all looking at it? So we are technically looking at t equals 0 here. Yes, no, maybe. Okay. So now we're just plugging in. So v of 0 equals, I'm going to go ahead and write this in vector form. What is sine of 0? Okay. And cosine of 0? So we get, okay. So we are at, so this is where I'm starting, and it is going to go towards zero 2 from this starting spot. So like it hasn't moved any horizontally, but it's moved up 2. And then it also asks us to find what? The acceleration. So what do we get there? -3, comma. Okay? So this time I've moved -3 in my horizontal and no in my vertical, so where would we end up? again, these have to have both magnitude and direction, so I have to put my arrows there. Questions on that? So like the point they give us is our starting spot, our vector is our ending spot, but again, that vector is from where we started, not from the origin. Are we all with me there? It's almost like you kind of think about it like your point is now like the new origin, right? Because that's my new starting spot. Yes, no, maybe. We'll go ahead and stop there today. I just don't, the next one isn't super long, but I just don't want to be cut off like in the middle of it. So we'll finish the last two examples that we have tomorrow, and then you'll have time to work on the last